All right, missed the transition there. I am still not feeling the greatest. In fact, I just took like an hour and a half nap. I was just feeling so worn down, and I think it just all kind of hit after my wife and I went to get groceries. It's just like I'm just tired of this. I'm tired of feeling this way. But I don't want to get down on it because I have this time off, so I don't want to just be concentrating totally on how I feel. So, though you have to listen to your body and go, okay, what's you know what's the right thing to do? you know, how's the right way to handle it? Okay, so anyway, let's get into day 8. I read this on the previous stream. Basically, you have to find antinodes, and so if I zoom in a little bit, they're basically you know pairs between all these different pairs of nodes that have the same letters. And so what I was thinking is that you have to find basically the length difference between the two. So like between this one and this one, and it's interesting because it's like, how do you, like, if I start here, the difference between its x position and this position is -1. If I started here, it would be 1. And so they could also be on the same line. I wonder, do they have that showing here? No, they're always, well, in that small example, that's true. I don't know if it exists where they could be on the same line, though there isn't any rule to say that they couldn't. At least I don't think when I was reading the problem that that's the case. So the thing is, part of me goes, this is it feels like it's kind of simple, but you have to be a little careful to go, how do you find the two on each side? Right? I think what you'd have to do is say the one on the left is like, well, it could be right underneath it too. So you can't necessarily, I'm trying to think of a generalized way to come up with how do you get all of the nodes. Like between two nodes gives you that line, and then you just have to say, well, I have to do it on one side of the line and the other side of the line. And so conceptually, I can see this in my head as to how you do this. You just have to pick two and then say, whatever you put on the left, whatever you say, you say is on the left side. This is maybe the way to do it. Is the one that is saying the line goes in that direction. So then to get one of the antinodes, you just apply that from the other antenna's position. And then to get the other side, you just say that's the left to get in, or you could just potentially flip it, I think. Flip because you can either go one over. Let me go back here. I think I kind of figured this out. Like with these two, if I wanted to get the antinode on this side, I would say, okay, I've got to go 2 over. So basically, I start, I'd say this is my start. What's the difference in the X here? And I would say that's 2. So I got to go 2 over, and then I got to go 1, 2, 3 down. 1, 2, 1, 1, 2. And that would be off. That would be off here, but you get the point. And then I just reverse it. Now from this node, so if I calculate, I say my left and right, that gets me that line definition. To get one antinode, if this was your left, you then start from the right, apply that transform, get the position, and then see if it's on the grid, and then see if it's uniquely an antinode. To get the other one, you start on the left, you reverse you flip the negative value. So you just multiply it by 1. Minus 1. And then that would make you go the other way. So actually, I think this is probably feeling not too bad, but let's get into it. Let's get some music going, as always. I got to start writing some music. That's the thing that I just realized is I just got to start like writing some simple background stuff, but that I wrote it, I built it, I created it, and that way I don't have to worry about copyrights. Hopefully, that I don't write something that's as similar as what somebody else did. All right, let's just do this. Let's follow our pattern. Actually, oh, nope, that's not what I wanted. That's what I wanted. After I shut down, I said, well, maybe I could just scaffold this stuff out, but I'm like, no. That is not what I agreed to. I said I was going to do no work on this stuff. I may think about it. I'm going to do no work on it. So, okay. Var unique antinode positions is equal to 0. L. I'll do the same thing here. Yeah, I don't want to do input.length because that bit me last time. Okay. I think with all these, all we have to do is store an antenna. So we have a public sealed record antenna, char frequency, an int x and an int y. Okay, so that gives us what it is and then where it's located. And so in this case, we're going to want a var antennas is equal to a new list of antennas. Then we go, well, sort of. So we'll say for each line and input, doesn't matter. What we want to find is for each var frequency in line. Wait a minute. Yeah, let's do that. Because we need to know where we're going as we go down. So we get a line, and then we say var, well, for each var frequency in line. Except that also needs to be a 4. And then this is frequency. Okay. If frequency does not equal a dot, which I'm almost positive, that's what's on it. Yeah. We then say antennas.add a new frequency at location fi. So actually, let's make that reflect. Okay. So now we have all of our antennas. Okay. Now I could... No, you got to go through each one. That's right. We also need a var max x, which is equal to input of 0 length var max y, which is the input dot length. We also need var unique antinodes, which is a new hash set of int. We don't care where they came from. We just care that they're unique. So what we have to do now is go through each antenna and then, let's just write it. For each var antenna and antennas. Var paired antennas is equal to antennas where the frequency is equal to the antenna that we have, and it's not equal to the antenna itself. So we want all the other antennas that have it. Okay. Var line is equal to now we can say for each var paired antenna and paired antennas. And now we need to say var difference is, we'll always start with the antenna. The antenna is x minus the paired antenna x, and then the antenna y minus the paired antenna y. Okay, so that gives us a point. Okay. Now, we said if we were looking at one and if that's where we started, minus the paired antenna, then to get our first antinode is the paired antennas x plus the difference at, item 1. Well, fine. That's fine. Actually, can we do... no, we can't. We can only say... Well, we could do an anonymous type here. We could say new. X is equal to that. Y is equal to that. And now we can say difference.x. That reads a little better. Okay, so now we can say for here, and we could have gone up, so we could, it's a plus either way, but we want to say paired antenna y plus difference y. And now we want to check to see if that's within the range. If first antinode. Could do the same thing here. We can just make a public sealed record node. Sure, do that, except we'll do that. And then we can put the node in here. There. And so then we say here new. Down here we could say new node. That. Except these are all positions, right? Yep. And so here we want to say this is also a new node. Okay. If the first antinode's x is greater than or equal to 0, and first antinode's x is strictly less than the max x, and first antinode's y is greater than or equal to 0, and first antinode's y is less than max y, unique antinodes is adding first antinode, except we're going to make this now nodes. And we don't care, excuse me. So we don't need this. We just need unique antinodes length or count or whatever it's going to be. So we can get rid of this one. Okay. So now we get, so that was the first one. Now our second antinode. We went from the paired antenna and we added it. Now we got to go the other way. We got to say new node, starting from the antenna's x position, x minus the difference. Yep. And then we do the same check here, which is repeated code, but that's okay. And we're done. I know I just said I don't like doing this, but we're just going to do it just so it shuts up. Okay. Don't need globalization. So let's rip through this again. We go through all the lines. We go through all the characters of the line, and then we determine its frequency and its position. Then we get the bounds. X is just one of the line lengths. Y is how many lines there are. And then we go through each antenna, and we get all the paired antennas. And the paired ones are the ones that have the same frequency but are not that antenna. Excuse me. And then for those paired antennas, we get a difference. The first one, we add on to the paired antennas difference, right? Actually, hold on. Let's say that this is the one I got. And so my paired antenna is this. If I follow my difference logic here, I'm getting This antenna is minus its X. So that's going to be -2, and this will be -3. The first antenna's node, if I go from the paired antenna and I do this, that's not going to work. That's just going to put us right back on this one. And the second antenna is going to put us right back on this one. So I think we want to reverse this. Like the paired antenna's position should be minus. Now, is that true? If this was our antenna and this is the paired one, we would get a difference of 2 minus 3. No, 3, because this is a bigger Y than this one. The Y increases as you go down. So now we would say the paired antenna is X plus 2, 3. Yeah, so these have to be reversed. So let's do that again. This one, and this is the paired. This would give us a 2 and a 3. Okay, so then we go to the paired antenna. We subtract 2, and then we subtract what is 3. So 1, 2, 3. So it would end up being here. Okay. Now here we add 2 and add 3, so we'd see it down here. If we reverse it so that this is the antenna and this is the paired, we would get -2 and -3. Okay. And so we go to the paired antenna, minus a -2, which is 2, 3. We come to here and we say -2, -3. So it works, I think. And the unique antinodes are just the nodes. All right, let's run a test and let's see what happens. Ah, crap. Let's get our input. Okay, so this one's, I think, said 14, right? Yeah, 14. It passes. Doesn't mean it's right, though. So we need solution day 8 input. Except we don't have that one. So let's see what. So day 8 says 336. Is that correct? It is. It is. All right. One thing I thought of too, as I was just ruminating on the problems, the one from yesterday where you had to, that kind of got me stuck a little bit. And if I go back to that one with like the, where is this? Yeah, this kind of math pow thing is basically trying to like have your slots be flags of power 2, 3, 4. This is the generalized version of it, actually. But what I was thinking of is, could you be a little bit more strategic and picking your, like trying to pick more of one operator than the other, because like if your numbers are small relative to the result, you probably need to do concatenations. Like if it's really small, if it's somewhat small, you probably need to get some multiplications there. If they're very close, you probably don't want to do either one of those and want to just start with adds. So you could say the first one I always want to try are concats, then mults, then adds. Or I want to do mults, then adds and concats, or I want to do adds and then mults and then concats, or something like that, and try to be a little bit more strategic in terms of which one you try first. Because as soon as you find an answer, you can stop. But I was like, okay, whatever. All right. So we got our answers and our notes. Let's commit part 1 of day 8 is complete. Now, how is part 2 going to mess us up? Watching over your shoulder as you work. Let's quiet that a little bit. I've watched the playthrough afterwards, and I've noticed that here, I'll turn this up just a little bit. There we go. I've noticed that the background music is not as loud as it is that I hear it in my ears, so oh well, whatever. By the way, if you're new to the channel, please subscribe. I would greatly appreciate it, trying to get to that first mile marker of 1,000 subscribers. So please subscribe. This is not usually how my throat sounds. I've just been fighting a cold. Anyway, part 2. What was I saying? Oh, the mics and the sounds and stuff. Anyway. Okay, so watching over your shoulder as you work, one of the historians asks if you took the effects of resonant harmonies into your calculations. Whoops. After updating your model, turns out that an antinode occurs at any grid position exactly in line with at least 2 antennas of the same frequency, regardless of their distance. That means that some of the new antinodes will occur at the positions of each antenna, unless that antenna is the only one of its frequencies. So these 3 T frequencies now create many antinodes. Oh. Unless that antenna is the only one of its frequency, which we've already... Get 7 out of the way here. Which we've already taken into account because we do our link query. Link, that's redundant. Language integrated query. TLA acronyms. So we already do that here because we do the for each and we don't include our own. So if we didn't find any other ones, no big deal. We just gloss over it. So I think what this is saying is you do these calculations here. You do that until you go outside of the map. And then you just keep hitting it, and you just keep creating antinodes. Like they're saying here with with this one, it's pretty simple to see. You would do the transform for this, okay? Then you do it again if it didn't go outside. Then you do it again if you didn't go outside. Then you do it again. Oh, it's outside, you stop. You go the other way. You do one, oh, you stop. So you're just adding on more antinodes. And you can kind of see that here as well. So how many unique locations within the bounds of the map contain an antinode? All right, so we're basically doing the same thing, copy pasta. We know that's not the best thing to do, but it's almost the same thing. So now what we want to do is say, we always look at the first antinode. there a way to do this so that I think what we could do is say, the first antinode is going to be this. Now we just make a while loop that we'll never break out of. Yeah, you need the, yeah. But we'll break out of it because of what we're going to check here now. And so let's come back up here and grab the logic. So we're going to say first antinode is actually the first antinode this, first antinode that. And if we're within the bounds, we do this. Otherwise, yeah, we break. And the break should get us out of the while. Okay, so this just keeps going that way to find nodes. Oh, while true. That's right. You have to... That just makes you spin. Again, a little dangerous, but we're assuming that by doing this logic, eventually we're going to get outside of the map, and then we just break out. Okay. So now we do the same thing here. We say our starting position is the other one. We say while true. And then we're going to grab this logic again. I'm going to say second antinode is the second antinode's current X. Yeah. And then we're going to grab this logic here, put it there. And then we're going to say else break. And that goes with that one. All right. If we do our tests, I'm trying to get my hands off the keyboard. I do that a lot. I try not to use the mouse as much as I can. Of course, sometimes the mouse makes perfect sense. So 34 is the answer now. Is that what we get? Failed. We only got 29. Crap. Huh. I thought my logic was airtight. Clearly it's not. Oh, wait a minute. Wait, I'm misinterpreting what they're saying here. Yeah, so that creates those two. This one creates that one. This one shoots out. So it's basically like, you can think of it as a gun that's shooting repeated bullets. So these three T frequency antennas now create... What was the difference between these? We're talking 5. So these 3 T frequency antennas now create many antinodes. Right. In fact, the 3 T frequency antennas are all exactly in line with 2 antennas. So they are all also anti... What? I don't quite understand this. I mean, I think it's because I'm not including... I'm making all of these, and this is what I'm counting. Is that in this case would be... If you threw this in here, I'd count 6. But for some reason, I got to count all these T's. But I don't think you just count them. Because, like I said, I am getting a difference of 5. But there's clearly 1, 2, 3, 4, 5, 6, 7. So it's not also just these. It turns out that an antinode occurs at any grid position, exactly in line with at least 2 antennas of the same frequency, regardless of distance. This means that some of the new antinodes will occur at the position of each antenna, unless that antenna is the only one of its frequency. I am not understanding how this problem is worded. So these 3 T frequency antennas now create many antinodes. In fact, the 3 T frequency antennas are all exactly in line with 2 antennas. So they are all also antinodes. I don't... Oh, okay, I think I just got it. No, I don't. Are all exactly in line with 2 antennas. So they are all also antinodes. I don't understand how... No, I don't understand this. I truly don't understand how this... In fact, the 3 T frequency antennas are all exactly in line with 2 antennas. What do you mean exactly in line? So they are all also antinodes. How? How? I don't understand the wording of that. That doesn't make any sense. After updating your model, it turns out that an antinode occurs at any grid position exactly in line with at least two antennas of the same frequency. That means that some of the new antinodes will occur at the position of each antenna. So you just say that basically when you find these pairs, because here you would make one, and this one. Here you would make one, so you include that one. But it's also unique, and so that's where you get three. Here you'd make one. Here you would make one. Here you'd make one, that's three. That will give you four. I don't think that doesn't make any sense because I'm only off by 5. Unless 2. No, that wouldn't do it. I'm wondering if you get overlap from some other because this goes down 2 over, down 2. So that would have already put one here. So even if we count all these 4 here, we'd put one here as a 5. So if you come over it with this, that's just another 5. You do the transformation here, that's just another 5. But how in the world do you cover these with antinodes? That'd just be 6 and 7. How do we get an antinode here? Oh, because of this. Okay. I still don't understand. I still don't understand how, if we get 29 and we're only off by 5. What I'm wondering is, am I hitting 2 of these already? Like 1, 2, 3, 4, 5, 6, 7. If I'm hitting 2 of them, then if I counted all 7, 2 of them are going to be hit by what I'm doing naturally, and that would give us the other 5. You always include the positions of the antinodes or the antennas that you're getting, if that's true. I guess there's a simple way to do this. We just add them in right away. We say, well, we can do this here. And then we say paired antenna position. What does this give us now? That passes. Okay, that must have been the case. Whatever. Okay. Let's go over here and run both. See what happens. Is that the right answer? That's the right answer. Alrighty. Close that. Git commit. Part 2 of day 8 is complete. So got a little gold star. Is this like a lake with a island or something? I can't tell. I can't tell what that is. Leaderboard. Am I on the leaderboard? No, I'm not. Ranger McSexy. Okay, whatever. Whatever. Okay, so let me fill up some coffee here, and I'm being a little bit better than what I was in the past. And that I brought some extra coffee down with me so that I don't have to run upstairs and get some more. Make sure it doesn't drip everywhere. All right. Let's move on to day number 9. Disk fragmenter. Yay! Compression. Another push of the button leaves you in the familiar hallways of some friendly amphipods. Good thing you each somehow got your own personal mini submarine. The historians jet away in search of the chief, mostly by driving directly into walls. While the historians quickly figure out how to pilot these things, you notice an amphiphod in the corner struggling with his computer. He's trying to make more contiguous free space by compacting all the files, but his program isn't working. You offer to help. He shows you the disk map, your puzzle input he's already generated, for example, a bunch of numbers. The disk map uses a dense format to represent the layout of files and free space on the disk. The digits alternate between indicating the length of file and the length of free space. So a disk map like 1, 2, 3, 4, 5 would represent a 1 block file, 2 blocks of free space, a 3 block file, 4 blocks of free space. Oh, that's what they mean by alternating. Okay. And then a 5 block file. Disk map like 9 represented 3 9-block files in a row with no free space between them. Each file on disk also has an ID number based on the order of the files as they appear before they are rearranged, starting with ID 0. So the disk map 1, 2, 3, 4, 5 has 3 files, a 1 block file with ID 1, a 3 block file, and a 5 block file with ID 2. Using one character for each block where digits are the file ID and a dot is free space, the disk map turns into this. Okay. The first example above, a 2 with a 3 space, a 3 with a 3 space, a 3 with 3 space, okay, represent this blocks. The amplifier would like to move file blocks one at a time from the end of the disk to the leftmost free space block until there are no gaps remaining between file blocks. For the disk map 1, 2, 3, 4, 5, the process looks like this. Okay. So we take all the ones here, we replace what this value is with so we just keep going over until we change the number, the identifier, or we change that we hit free space. So we put 2 here, we put 2 here. We then try to find the index of the first free spot. The first example requires a few more steps. So in this case, we have 9. We throw over a 9. We throw over an 8. Throw over an 8. Throw over an 8. We skip this. Except when you skip, I think when you skip, like here, you're taking this one and you're putting it here. This just, are you just not doing anything because it's a free block? Now you come here and you see you got a 7. So that got moved here. This one gets moved here. This one gets moved here. We see a free block. Now we see a 6. Well, that has to go to the last free block. This one goes to the last free block. This one goes to the last free block. And so you basically you move from the end of the string and you take a look at the character. If it's a number, in other words, if it's not a free block, you go from the beginning of the string and you do an index of a period. And I believe index of in C# will give you a -1 if it can't, well, no. We have to be careful here. Like this, when we're in this position, we can put this one here. This one can put it here. This one, we either don't find free spot, we don't find free space, or the index is greater than where we are, because then we went over and we've moved everything over to the left now. The final step of this file compacting process is update the file system checksum. To calculate the checksum, add up the result of multiplying each of the block's positions with the file ID number it contains. The leftmost block is in position 0. If a block contains free space, skip it instead. Continuing the first example, the first few blocks positions are 0, so 0, 0, 1, 0, 2 times 9 is 18, 3 times 9 is 27, so on. The checksum is you just add those all up. And so if you see a dot, you just don't do anything. Be careful copying and pasting the input from this puzzle. It is a single, very long line. Oh, I mean, it looks intimidating. Because, well, how do you... Yeah, you gave us one that only gives you... Oh, this is tricky. It's not as... The reason I say it's tricky is because you can't use, like, this is the line, which gives you basically what is on the disk. But if I zoom in on it, it's saying the first file has 4 bytes and it has identifier 0, and then there's 8 free spaces. The second file has an identifier of 1 and takes up 7 spaces. So it's a file identifier 1, size 7. This one is and 5 free spaces. Then this one is file ID 2 with 7 spaces and so on. And so what you're going to end up having is identifiers that are not just single digits. Using one character for each block, where digits are the file ID and X is free space. Using one character for each block. This is what I don't like about how Random.Code works sometimes, is that they clearly are not giving you the what do you do when you go over 9. Right? And so if you literally use this, what would happen if you have another pair here at the end? You can't put 1, 0 because you couldn't tell just by laying it out that way. Is it 1 or is it 0? Or is it a 10? Unless you start doing some really, really funky handling. And so I don't think it's... my guess is that this is saying that you are taking the identifier, which in our case is the identifier 9. And so I think what you want is, we have the concept of a block, right? And the block can either have an identifier, what they call this primitive obsession. So we have an identifier, which is actually going to be probably, we'll make it a long, but it can be an int, whatever. It's your identifier. Or it's free. So it doesn't have an identifier. And so what our array is, or which will be a list, is just a list of blocks. And either the blocks have identifiers or they don't. So rather than trying to literally stuff the identifier into a line like what you're seeing here, we have to abstract it up. This is just a representation, is the way I'm interpreting this as. And so I think that's the way we want to do it. Is we're going to have a block, and the block can or cannot have an identifier. And that way we can say, okay, kind of do the same thing we did before, which is to say, we're always going to have free space. And at some point, as we move these over, as we're trying to find the first block where the identifier is null, that index is going to be after what we put an identified block on. Let's do it. When you're whistling to your own songs. So we're going to have a public sealed record identifier with an, we'll just say it's an ID, okay? And a block can have an identifier. We'll call it the owner. So if the owner's null, that means it's free. If it's not, that means that we've actually put something in there. Okay. Shut it up. Okay. So actually, in this case, we are not doing oh, for God's sakes. I know what I'm doing here. Okay, so this is a little bit of a rant. This is where I can't remember if they were going to put it here or if they were going to put it here. But where they were going to put that basically damn it operator, I think either on the type or the input, but either way, what that would do is it would guarantee that that was not going to be null. And so it would do, and why it just do that? And then it shuts it up. And I get why there's so much debate around that, and they basically deferred that for being something that maybe will come in the future, if ever. That would have been nice, because then I wouldn't have to write this, and then I wouldn't have had to bitch about it while I'm doing this. So, actually, hold on. I mean, I don't want to. I don't want to run the risk of flatlining my input here. Okay. So there we go. Okay. Okay. So we have blocks, we have identifiers. So what we want to do is we basically want to run through the file, run through the input in half. So we want to say for int is 0, I is less than input dot length divided by 2, I plus plus. I am assuming oh, we can't. Okay, that's exactly what I was going to say. Is my assumption going to make an ass out of, well, not you, but just me? And so you can't do that. You have to go at this in two number chunks. And make sure that you don't go off of the length of the string. Right. And we're also going to need a var identifier is equal to 0L. And because we're going to need to numerically increment that identifier as we discover so let's do that. Let's just say let's do this. Var index is equal to 0 while true, our very best while thing, we're going to say well, what we can do is we can put that in the while loop. We can say while index plus 1, and let's be explicit here, is less than the input length. So if we just got a 2, no, we can't do that because we could literally get a 1. We're not going to, but if we want to think a little defensive here, we could end up in the position where we get a 1-by-1 mapping. That's just saying we have one file of a particular size. This is assuming we'll always get, what are they calling this? A disk map of length 2 or greater. And actually, if you had only one file, the checksum would always be 0. Because if you go down here to get the checksum, you would never be able to, because the position 0 times, it would always be an identifier of 0. Like even if you found, like it said, there was 9 blocks for the first file, which would be identifier 0. It'd be 1 times 0, 2 times 0. The checksum would always be 0. So I'm okay with this because we know we're going to get more than that. And then we're going to say here that index is plus equals 2. So we're always going to just keep shifting it over from 0 to 2 to 4. And let's say we had a 5 files. So if we had 0, we'll get 0 and 1. And then we say index is 0 plus 2, 2. We'll get 2 and 3. We'll get index is 2 plus 2 is 4. We'll get 4. This one's 5. 5 is not less than the length of 5. And so it breaks out. Okay. So we get a list of blocks. The problem, yeah, I just realized this too. This won't work because the problem is, yeah, let's just do it. What are we calling this? Of our format is going to be if index plus 1 is less than the input length, that's fine. Now, if we're at 4, this logic I'm about to add would handle it. If we then go to 6, we're then going to say if index is greater than or equal to the input length, we break. Okay, so the format, if this is true, then what we get is in the input, we get it at the index. And we also get input index plus 1. Else, let's put that in a public sealed record. Format int file size int free space size. So in this case, you can say new format of int.parse of index, no, of input index. And then we do the same thing here to say what the free space is going to be. Right? Index plus 1. Yes, I know. Culture, info, current culture. Oh, yeah. Is there a convert to int 32 giving it a char? But that's probably not what we want. Yeah, we don't want to literally take, and I know there's this trick that you can do, like with numbers, you can subtract them, right? You can ASCII number to int integer. There's a minus 32 or something, isn't there? I thought there's this one trick, and I'm forgetting. This is not what you want to do. Char number to integer, C#. Yeah. It's minus 47. Okay. So we don't need any of this crap. We're going to assume minus 47. Or you could be saying, like they are saying, minus like that. I knew there was this one trick. I just couldn't remember it off the top of my head. Okay, else we're going to get a format where it's this, and it's just going to literally be 0. Okay, so we have now the format. And now we need to put in, we're going to see identifier ++ here too, just because we have to, well, we only need to increment it technically if we don't break out. So now we need to say for var let's just say I. And this is wrong. We want format dot file size. And what we want to put in here is in the blocks, we want to add a new block which has a new identifier of identifier. That reads like crap. And then what we want to do is say for var I, except now we want to get the free size. We're going to put in just null space, essentially. And so now we're adding in all the blocks that way. Actually, this will handle now a disk map of 1, because we're going to assume 0. If you give us 1, well, then we're just going to, we'll process it correctly, which is stupid, but we can do it. All right, so now we've got the blocks. And now what we need to do is go from the end of the list and move and just keep going backwards, skipping over empty space and taking that identified block and moving it over into the first space we can. If we find free space, as soon as we find free space that exists after where we're trying to, like if we say here, we're here, find me the first free block. If that's before us, then we can pick it up, put in a free space there, and then move that into that spot. If we find that it's after, we stop repositioning. Okay. So now we're going to do another. What we're going to say here is var file block index is equal to blocks dot count. No, count. Okay. -1. So what we want to do is say, we can just call this block index. That's where we are. So we're going to say var block is equal to the blocks at block index. If the block dot identifier owner is null, is not null, because those are the ones we care about. Now we need to find the first free block. Free block index is blocks first, the first one. I'm just going to assume first. And what I want to find is the first crap. Okay, fine. We'll find it and then we'll get the index of it. So we want to say blocks index of the first free block we find where owner is null. Okay. If free block index, it can't be us. It's got to be strictly less than the block index we're on. If that's true, then we can effectively switch them. So actually, I want to var free block. I want to preserve this. I could have just done a local thing for me. So if the index is less than that, then we can say blocks at free block index is equal to our block. And then the blocks at the block index is now just the free block we had. So we've effectively switched those two around. I'm pretty sure the way this works, although I could be proven wrong, that this is always going to escape out because we're just, well, we have to block index minus minus. That's pretty crucial. Else, we break out. Because if we ever found a free block index after a block that we're currently on. That means we've pushed everything over that we possibly can. And now we need the var checksum. And this is definitely going to be an L. We might even need to make it bigger than an L, a long, but we'll assume this is enough. And now we can say here for each block and blocks, if block is null, we break, because we don't need to do any more calculation. Otherwise, we're going to say checksum plus equals what is the actual algorithm we're supposed to do here. Wait, did I save this? Day 9 input.txt. Oh, that's fine. Okay. Add up the result of multiplying each of the block's positions with the file ID it contains. So we're going to have to do this as a for, because we need to know the index. So we take the index, multiply it by the block's owner ID. And then we return the checksum. Does this work? Highly doubt it, but you never know. The only way you're going to know is if you try. All right, so it's saying with this example, solution day 9, run part 1 of just the input is what? That. How bad did I mess it up? Oh, passed. I'm not making this up. I seriously am surprised when it actually works off the bat. Of course, it doesn't mean it actually worked. It just meant that our test case worked. Right? So let's get 9 in here, 9 in here. We gotta make sure it's a day 9 input, 9 input. Let's comment that out for now. Oh, and we don't need to read all text, right? There we go. What does this do? Ah, crap. I never got the value. Hold on. Let me do that real quick. Just get that in the notes. Okay. So we got that. You notice it took a while, though. I'm wondering which spot was the hardest one to do. I'm kind of curious. I'm kind of curious if it's, my guess is there's basically 3 spots of what I've done. it's getting the list of blocks. I think this actually goes pretty fast. This one, yeah, this could get a little ornery because you're going through and you're finding the first. What I'd really like is first with index. Or I'd like an index of like I want to get is there like an item of like I'd like to really get the item and where it exists based on is the first one where the owner is null and tell me where that index is as well. I'm thinking this is where most of the work is, but not really. I mean, as soon as I don't know. It'd be interesting to see where the holdup is here. But we have the first part. Okay, let's go to part 2. Now, how much harder is this going to get? Upon completion, 2 things immediately. Wait, before we do this, how to do this? Need to get the remaining coffee here. Leave no coffee left behind. With my alma mater, Marquette University right there. I think the education system as a whole needs a massive rethink in terms of how technology works and how that can help and affect and bring the price down substantially. But I am also still proud of the work I did and going and getting my degrees and stuff like that. So with that, okay. Upon completion, 2 things immediately become clear. First, the disk definitely has a lot more contiguous free space, just like the amphipod hoped. I'm sure it did. I don't really know. I don't have a visualization of what that looks like. It'd be interesting to see just how big this list got. Actually, I'm just curious. Let's run this and let's see. How many blocks are there? 95K. It's not that big. I mean, it's not a small list, but it's basically an array of 95,000 elements. So, not too bad. Okay. The eager, let's see, second, contiguous free space. Second, the computer is running much more slowly. Maybe introducing all of that file system fragmentation was a bad idea. The eager amphipod already has a new plan. Rather than move individual blocks, he'd like to try compacting the files on his disk by moving whole files instead. This time, attempt to move whole files to the leftmost space of free space blocks that could fit in the file. Attempt to move each file exactly once in order of decreasing file ID number, starting with the file with the highest file ID. If there's no span of free space to the left of a file's order, the file does not move. You're an ass. So you notice that they had to actually go all the way to 4.4. Yeah, I'm almost I'm trying to keep these under 2 hours. I'm almost at time, and I'm feeling like this is probably a good place to stop. I am going to probably do some streaming again tomorrow afternoon and potentially tomorrow evening. I might actually come back to this tonight. I'm not sure. But what I did in my representation is I have the literal blocks identified by the file identifier. Arguably, to save on space, is you could put the you could say like this slot actually represents a file of this size, and this slot actually represents on your file system free space of this size. It doesn't have an identifier, but it has this much space. The problem with that is the differencing. Because if you did this, then you're saying, well, that is a section of 3. And what I need it to be now is I need to move this file with size of 2, put it over here, subtract it. So now that is a size of 1. Actually, and I get that the check something is true, although I'm short-circuiting it because I know that I'm pushing everything over until I can't anymore. So as soon as I hit a free space, I can no longer, there won't be anything afterwards, so I don't have to keep going through them. With this, it's the same thing, except I can't break out. And so I'm thinking the way to maybe do part 2 isn't using the same exact types and using the same exact representation. It's to basically say, have some type that says, does it have an identifier? And whether it has an identifier or not, how big is it? So either if it's an identifier, it's a file, and it'd be a size 4. If it doesn't have an identifier, it could have a size 3. Okay. And so then what you would do is you now have a list of representations, of partitions, or whatever you want to call them. I don't know exactly what the type is I want to call it. And then it's just going to be file free, file free, file free to start. And we do the same thing. We go from the end and we say, find the file. We know it's of a size. What we want to find is the first free slot that is equal to or greater than my file size. Okay. And we have to be really careful here because I think in this case what we're going to actually have to do is go all the way to the end and just, maybe. But we take a file at the end and we say, is there anywhere to move it at the beginning? If we find that, now we have to do some math. We're now going to put that file at the location. We're going to insert it right at that index. And so that should push over that one. But then what we also need to do is look at that free space block section. Call them sections. Either maybe just call them sections. I don't know. File sections. Disk sections. Maybe that's the right thing. Maybe we want a public sealed record section. And a section has an identifier, maybe, who's the owner, and then an int of size. So maybe a little different. Okay. And so we look at the difference. In this case, a 9 had 2, so we could take up 2 here. And so what we need to do then is this node, we need to change it with a new section that has a null owner and a size of what the current size is minus the size of the file. And actually what we could do is say if we completely take it up, we wouldn't even try to do this if we can't find it. But if we do, if there's a remainder of that, then we actually will change that section to a new section of a different size. Otherwise, we just remove it at that index. We no longer have that there. With 8, it's a size 4, and there is no 4 over here, so we skip it. 7, we see, there's actually 2 here, but this is the first one. And so, and we also have to null out the, we have to put where we took the file, and we're going to have to put in a new section there that says it has no identifier and has the size of whatever the file was that we moved over. Here we would say same thing, it's going to be a size 3, and we're going to put this 3 here, and then we actually remove that. No, because we don't need it anymore. We go look at 6, that's a 4. Wait a minute. Are you seeing what I'm seeing? Seven moves to here. Why doesn't 6 move over to here? And I get a 2, like 3 can't. For 2 can though, because there is a oneer over here. And then you would just keep going through all of your files of decreasing. Yeah, so what you want to do is go through and say, find me the file of decreasing identifiers. Because once we've moved, like if we moved like here 9 and we moved 9 here, that's because there was no, you're not going to suddenly make space. You're just going to fill it. So there's no reason to now do this again and try to do the calculation. You can skip it. We're just going to go through decreasing identifiers, finding where they are, and then determining if we can move them. What I don't like, though, is this, because it says 7 moves here, but this 6 is 4. Oh, okay. Sorry, it took me a second to realize why it didn't, because on this line, there isn't 4. We haven't moved 4 yet. 5 doesn't move. 4 now moves. 6 could move, but we don't recursively keep going back and seeing if we can move them over. Arguably, you could move 6 now. You could actually move 8 over once you move 4 over. You could put 8 there. And maybe that's part 3. But not today. So, okay, now that makes sense. That took me a second to realize I was just not getting it because I saw this line. I saw this line and then I saw this line. I'm like, wait a minute, there's space here, but no. Because you can't move that over, you can't move that over. 4 can, it can go here. 3 can't. You would look at 2 then, that can, 1 can't, 0 can't. Technically, you only have to do it for identifier down to 1. 0's at the beginning and it wouldn't move. Okay, I think I have the algorithm in my head, but I'm not going to do that right now. I'll come back to this and do it. The checksum part then is also a little interesting because now what you need to do is say, look through all of your sections. And if the section has a identifier, then you have to do that little loop to get the checksum based on your identifier and where you're currently at on disk with the blocks. If you're not, you simply update the block count. So like what we're doing up here in run part 1, the block count, we'd have to now like use the block index idea and come up with a way to say get the checksum based on like if it's a file. Well, if it's a file, then you do the checksum. Either way, you're going to increment. Well, if it's a file, you do the checksum, and that will automatically increment the block index as we go through it. If it's space, then we just simply need to increment the block index by how much free space is there. Okay, I think that will do it. That'll be interesting. I'm wondering with the algorithm I just came up with in my head, if it might be somewhat fasterish because we're not actually storing each block. We're storing a section that represents a file or a section of free space. It'll be interesting. I'm almost wanting to do that right now, but I'm not. I'm going to stop. I'm going to stop for now. And I might come back tonight and just at least finish part 2 of day 9 and then get into day 10, just to keep things moving along. But I would probably do a short-ish stream tonight. Either way, it's either tonight or tomorrow. So with that, I'm going to stop. Thank you for watching. If you're watching now or you watch in the future, either way, please subscribe. I would greatly appreciate it. And with that, I am going to stop the stream. Thank you all for watching. Take care. Hope to see you in the future.